Hey, I want to, Ian Allred here. I want to work a couple problems where we do compound interest and we solve for R and T. Now, maybe not explicit as that, but the two formulas we have the compound periodic and we can work with this guy. We've already figured out how to solve for A and P, but the other thing we might solve for here is T. Now, we could have situations where we have the information to solve for N or R, but on this particular formula, I'm not going to ask you for either one of those. We also have the continuous formula where we solve for A and P. But because of the position of R, I may have situations where I would ask you to solve for R or T. So this is after we have the information on logarithms, okay, and solving equations where we have to find the exponent. So let's see a quick example. So over here, let's just kind of break this into two parts. It might take a little bit more room than we need. But let's say we want to have $30,000, but we're starting with $20,000. And our rate is, let's just go with something simple, 5%. And it's compounded, let's go with monthly. So we might ask ourselves to find T. So we know what we want to start with $20,000 and end with $30,000. We know that the account we're putting it in earns 5% interest compounded monthly. We're trying to figure out how many years it takes to make that jump from $20,000 to $30,000. So as we set that up, let's use some colors. 30,000 equals 20,000. And we'll have 1 plus 0.05 over 12. This is a problem I have of drawing lines before everything is done. But up here we would have 12t for n times t. So now we want to solve for this t. So we got to get that exponent out where we can work with it. So we'll divide both sides by 20,000. So 30,000 divided by 20,000 is 1.5, 1.5. And then I'm going to go ahead and take my calculator and figure out what this other part is. The 1 plus 0.05 divided by 12. Make sure your calculator is on when you start mashing buttons. So that is, well, it might not be too bad, but 1.00416667 raised to the 12t. So hopefully you can leave that number in your calculator, but if you need to rewrite it, you can. But keeping in mind that this exponent up here is what we're trying to find. We're trying to find the t. So we're trying to get the exponent out of there. So let's use a logarithm. Let's actually use the natural log. Let's take the natural log of both sides. So we'll have natural log of 1.5. So if you remember in solving equations, if we do it to one side, we can do it to the other. So we'll have the natural log of 1.00416667 to 12t. And we can now pull this 12t out front. Remember that property? So I'm going to go ahead and figure out what the natural log of, well, let's just leave it there for now. Natural log of 1.5. And over here I'll have 12 times t times the natural log of 1.0041667. Now I'm trying to find t. So I'm going to divide by the 12 in the natural log here. I'm going to put all this in the calculator in a moment and get a decimal. You could do a decimal earlier on and carry it through. So I've got the natural log of 1.5 over 12 times the natural log of 1.0041667. So I'm going to put that in my calculator. So we're going to get an answer that looks like about 8.13 would be t. And remember, that's years. So we should ask ourselves, is that reasonable? And if that's the case, I mean, we just really want to check ourselves. We could come back up here to where we set up the formula, to where we've got the green thing. We could plug that 8.13 in right here and see if it comes out to 30,000. Now we did some rounding, so it might not come out exact. Okay. So we could check ourselves, but that seems reasonable. It's not less than a year. It's not 1,000 years, so maybe it's reasonable. So let's do something similar with the continuous interest formula. Let's come up with some new numbers though. Let's say we're going to start with 10,000 and we're going to end with 40,000. And we're going to go ahead and give this thing a time of, let's make it 20 years. So what we need to do is we need to find R, which is the rate. So we're going to go ahead and set this thing up. We know that we've got 40,000 equal to 10,000 times e raised to the 20r. Okay. So we can divide both sides by 10,000. That will give me 4 equals e to the 20 times r. So once again, I could do quite a few things here, but if I take if I just change this to a logarithmic equation, convert it, I would have, let me see if I want to do that. Yes, I could have natural log of 4 equals 20 times r. So I can even get a pretty nice exact answer here of natural log of 4 over 20. Okay, but I'm using my conversions between log and exponentials to give me a way to get that exponent out so I can solve for it. So let me see here. Natural log of 4 divided by 20. So let's see what type of answer we get here. We get 0.0693, which is an R, which is in decimal form, so that may seem a little bit weird, but that's about 6.93%, which kind of sounds good as a rate. So in both these examples, what we did was we went through and we tried to find a way to get that R or that T out of the exponent position so that we could solve it. Okay? And we did that by either, in this case, on the first one over here, taking the natural log on both sides, which lets us use a property to pull that exponent out front. That was one of our properties of logs. On the other one, we actually simply just converted it to a logarithm. And both forms or both methods are pretty useful and could be used at different times. All right. Thank you.